Good afternoon, ladies and gentlemen. My name is Ilya Krivovyas. I will present to your attention the research work Prediction of Robot Movement using Sliding Figures. This work was carried out during the last 3 years, and during this time I was awarded various awards for certain parts of work. I would also like to thank my supervisors who actively helped me with this work. In the modern world, sound visualization is used in flow detection systems, in the field of entertainment, for example, fountain shows. Various physiotherapeutic methods of diagnosis and treatment are based on the ability to oscillate biological tissues and biofluids of the body. Currently existing methods of sound wave visualization testify to the vast possibilities of the practical application of sound visualization methods and their relevance. Our interest in the visualization of sound waves is caused by the fact that we want to use them to move the robot in two-dimensional space. The first experiment for visualizing sound waves is the Rubens tube, which is based on the connection of sound waves and air or gas pressure. The pipe is filled with gas in such a way that the gas slips through the holes, burns. A standing wave is formed in the tube using a constant frequency. A variant of visualization of sound waves is obtaining an oscillogram, spectrogram, and energy spectrum. Obtaining sliding figures with the help of wind instrument. Wind physical instruments are resonators that are provided with devices to change their resonating ability. When playing a musical instrument, such as a trumpet, sound must be of the same amplitude and frequency and the noise duration. Necessary elements of obtaining sliding figures are the presence of a speaker and a frequency generator. An example of visualizing is the computation of sliding figures due to increased frequency. One of the ways to visualize sound is with the help of computer technologies, for example, programs Chaos Vision, Flat Audio Spectrum, Music Visualize, and others. The main advantage of this method is the ability to carry out complex processing of the sound image. For experimental work we need the following raw materials and tools: heat gun with silicon glue, metal bolt with nuts, dynamic, a laptop with access to the internet resource with the frequency generator, a square sheet of fiberboard 20 on 20 cm. With the help of the device we obtained 12 sliding figures of different structures and established that the most successful material for obtaining sliding figures under the conditions of our experiment is the fiberboard sheet. Sliding figures were obtained as a result of the experiment were compared with literary sources, and the identity was confirmed. The robot motion planning algorithm in two-dimensional space included path planning, and this task mainly includes 3 aspects. First, the planned path must run from a given starting point to a given ending position. Secondly, this path should ensure the robot's movement while avoiding possible obstacles. Third, the path must pass among all possible paths that satisfy the first 2 requirements and be in a certain sense optimal. The formulation of the problem is reduced to find the smallest number of necessary steps to get the robot from the initial to the final location, or if it's not possible, the robot will inform that it's not possible. The version of the implementation of the task of finding the shortest path is implemented by us in the C++ programming language. The principle of robot movement can be described as follows. If the robot is at the starting point, then it sends a sound wave with a specific frequency to estimate the distance to an obstacle for a two-dimensional space limited by a wall. The reflected signal is returned to the robot, and relative to the frequency, the sliding figure is formed. If the frequency of the sent and received signal changes, then the sliding figure will also change, indicating an obstacle or a wall in front. If the frequency of the sent and received signal is unchanged, it indicates that the robot can start moving. To plan the robot movement in two-dimensional space, we wrote a code in C++ that was tested on a practical model of the robot. The advantages of the proposed motion systems are as follows. Before starting the movement, the robot can take into account all possible paths of movement from the starting position to the final position, instead of analyzing only one track, and choose the optimal route according to the distance and number of obstacles. Move in space not with the help of a video signal, but with acoustics, that is, visualization of sound waves. After all, the shape of the sliding figures will change when the sound wave meets an obstacle during the movement of the robot in space. After standardizing them concerning the shape and frequency of the waves, it will be possible to estimate the length of the path and the distance to the obstacle. Thanks to this, the robot movement can take place in an opaque space and, with the help of acoustics, detect even tiny obstacles on the way, which would be invisible for a typical video signal. The main achievement of our work is the possibility of practical use of the physical phenomenon of visualization of sound waves for predicting the movement of a robot in two-dimensional opaque space.